Okay, we wish to begin our discussion about forces, masses, and acceleration. And we're going to begin by first off discussing the whole concept of force diagrams. Now, you've already learned about force diagrams in statics. And the idea is that you take an object and you draw all the forces acting on that object. And then you determine an XY plane. And then you write out your force equations based on those. But I want to redefine a little bit a couple of things that have to do with forces. The first concept is long-range forces. Now, long-range forces can act at a distance. And so there's going to be really one long-range force that we're going to work with in this class, and that's gravity. Other long-range forces do exist. Electromagnetic forces are also long-range forces. For example, a magnet can be a certain distance away from a nail and still attract it to itself. In the case of electrostatics, you could rub a balloon against a sweater and it gets charged up, and then if you hold that near your arm or even lift up a piece of paper with it, you can attract the hairs on your arm or lift that piece of paper without actually touching the piece of paper. So those are forces that act at a distance. But again, the only one we'll really be working with any kind of frequency is gravity. We may work with a magnetic or electrostatic force in one or two problems through the semester, but not really much. Short-range forces need contact. They need physical contact. Now, this is a really important concept because the idea here is that a short-range force can't work unless it's touching the object. And so when you look at an object, for instance, a book sitting on a table, that book sitting on the table, it only has one thing touching it, and that's the table. So no other forces except for gravity, which is the only long-range force we're working with, can act on the book. It's got to have physical contact to be acting on it. So the trick to this, or the key, is that if the object isn't touching it, it is not exerting a force upon it. So exerting a force or touching it, these are going to bring up a couple of other things. First off, the whole concept of due to. Forces must always be due to a thing. This has got to be a physical object, not a concept. It's got to be a physical object. Even the long-range force of gravity is due to the Earth. Or if we're talking about a spaceship going around another planet, there'd be a gravitational force due to the spaceship, a gravitational force due to the planet. All of these things are physical objects. So if it isn't a physical object, if it's a concept, it's not exerting a force. It has to be a physical object. So as you look at what's touching it, only some object touching the book, and in this case the book is only being touched by the table, only an object touching the book can exert a force on it, except for the Earth and gravity. And then there's this whole concept of acting on. If I'm drawing a force diagram for the book, then all of the forces are acting on the book. Are there forces acting on the table? Yes. Are there forces acting on the floor? Yes. But we're only concerned with the forces acting on the book when we draw a force diagram for the book. Now, if I were to draw a force diagram for the table, then I would also be talking about, in that case, forces acting on the table. Are there forces acting on the book? Yes, but I'm not concerned with the forces acting on the book if I am doing a force diagram for the table. Which kind of brings up Newton's third law. Newton's third law is the whole concept of action-reaction pairs. Okay, action-reaction pairs. Newton's third law always comes in pairs, and I'll oftentimes label those as N3L, Newton's third law pairs. And the way you know a third law pair is you take whatever it's acting on and whatever it's due to, and you switch the two. For example, there's a normal force due to the table acting on the book. That's the action. The reaction is a normal force. It's the exact same kind of force, same size, opposite direction. A normal force due to the book acting on the table. So Newton's third law pairs are simply a reversal of the due to and the acting on. So let's do a force diagram on the book. And I'm going to look at the book from the side. And I like to do my forces in blue. And so there are two forces acting on the book. The first one is gravity, so I label it mg. I'll always label gravity mg or w for weight, which is, of course, the force of gravity. So this is a gravitational force due to the Earth. That's a thing, it's a physical object. Of course, it's not touching the book, but that's all right. It's a long-range force, the only one we'll work with any frequency. And since we're drawing a force diagram for the book, it's going to be acting on the book. One thing to note is the Newton's third law reaction to this would be a gravitational force due to the book acting on the Earth. So if this book weighs 1 pound, then the book is exerting a 1 pound force on the Earth. That's Newton's third law. We'll get into gravitational forces more later on. Then there's another force. This is the normal force, and I'll always label my normal forces F sub n. There may be other subscripts if there's other objects. So F sub n. I don't use the capital letter N because that's the symbol we use for Newton's. And if I use capital N for the normal force, it can get confusing. So this is a normal force due to the table, because that's the only thing touching the book. Due to the table, acting on the book. So those are the forces acting on the book. Now I might want to, at this point in time, create an XY axis, and I'll try to do most of my axes in green. And it makes sense to use a standard XY axis in this particular problem. We'll get to the equations a little bit later on, but this is the force diagram for the book. Okay, there's a normal force acting on the book, and there's a gravitational force acting on the book. Let's do another example. Let's talk about a ball. It's already been hit by the bat. It's on the fly, heading towards the outfield. All right, so what are the forces acting on the ball? We're going to neglect air resistance in this example. So there's my ball, right? It's baseball. There's my threads. All right, what are the forces acting on the ball? Well, of course, we have a gravitational force. So this is going to be gravitational force, which I'm just going to shorten to gravity, due to the Earth. And I'm not going to write due to much anymore. I'm just going to write dt, due to the Earth, acting on the ball. And of course, I'm writing AO for acting on. And this, all of this is what I refer to as defining or describing the forces. And this is something I'm going to want you to do, especially on quizzes. All right, so it's a gravitational force due to the Earth acting on the ball. Well, the ball is on the rise. All right, so it's moving. I'll use purple for the velocity here. It's moving in that direction. As I look at the forces, I want to say, are there any other forces? And my answer is going to be no. There's nothing else touching the ball. We can talk about air, but we're neglecting air resistance. The bat is no longer in contact with the ball. The catcher's mitt, or the outfielder's glove, is not in contact yet with the ball. There's nothing else acting on the ball. And so mg is the only force acting on the ball. So if I draw an XY axis again, I'll use the standard format. There's only one force acting on this ball, and it's in the y direction. So if I wanted to look at the ball's acceleration, and I'll use red for acceleration, the acceleration of this ball is down. This is the acceleration of the ball. Yes, it's moving up. So there's a component of the velocity to the right and up. So here is v sub x, and here is v sub y. But remember from projectile motion that only v sub y is affected by gravity. V sub x is constant. And now this makes sense along with our force diagram. Acceleration affects velocity. There is no acceleration in the x. So the velocity in the x direction must remain unchanged. Only the y velocity is changing. So mg is the only force acting on the ball. All right, here's a system. This particular system is in static equilibrium. And as I'm looking at the forces acting on the bar, so there's this bar here, and you'll notice I've labeled the weight W. All right, that's actually a small w. It's a little hard to tell in that diagram. So there's a gravitational force W. So this is gravity due to the Earth acting on the bar. There's also a force over here on the left-hand side that's caused by the pin. Now this will be a normal force, and it's very difficult for us to determine if it's a round pin, what direction is that normal force. So I'm just going to label it A sub x and A sub y. And these are both normal forces. I'm just going to call it a normal force, singular. That's just the components, the x and y components, due to pin A acting on the bar. Now the interesting force then becomes the one over here on the right-hand side. Now, the big block, capital W, is exerting a normal force on the bar. But in what direction? If I look at a tangent to the corner, there are an infinite number of tangents because the shape of this corner is such that the tangent, which is the derivative, is not defined. You can't define a derivative at a sharp corner. So anything can be tangent. Well, that's where I have to look now at the block W. That's the surface. And normal, as you already know, means perpendicular. And so there is a normal force, which I'll call Fn. So here's a normal force, and it's due to block W acting on the bar. I guess I don't need to really call it W. So due to the block acting on the bar. And the angle is such that it's perpendicular to W. All right, so that's perpendicular. So this is alpha. This is going to be 90 minus alpha. And so as I looked at this, if this is 90 minus alpha, that's got to be alpha. So alpha is this angle in here. So there's the angle alpha. Same as this angle with respect to the horizontal down here. Same angle alpha. All right. I'll let your geometry give you more information there. That's going to be the angle that we use to describe F sub n. Then if I look at the forces acting on block W, I'm going to find that there is a weight, capital W. This is a gravitational force due to the Earth acting on the block. There's a normal force, F sub n, a normal force. It's due to the incline acting on the block. And I better call this Fni for the incline, because I already know there's another normal force here, Fn. Now, look at Newton's third law. Normal force due to the block acting on the bar. So this must be equal in magnitude, opposite in direction. And it's a normal force due to the bar. We switch the due to and the acting on the block. We switch the two of them around. Okay, so normal force due to the bar acting on the block. This is a part of a Newton's third law pair. And the normal force due to the block acting on the bar, this is another Newton's third law pair. Right, so there also would be a frictional force. I don't really know if it's up the incline or not. I'm going to actually put it up the incline. Now, frictional forces, I'll just label it F, are always parallel to surfaces. So this is a frictional force, which I'll just call friction, due to the incline acting on the block. Right, so you'll notice this is a nice diagram because we've got a couple of the forces here defined now. Normal forces are one kind of force we're going to use. Gravity is another kind. So we know normal forces are perpendicular to surfaces. Friction will always be parallel to surfaces. And of course gravity. And then the other kind of force that we're going to have is tension. And we'll see this in the next example. So as we look at this situation, you can see tension is going to exist on block A and on block B. All right, now block B is pretty easy. There's a tension up, and there's an M sub B G acting down. So I've got gravity due to the Earth acting on block B. Now since they're both blocks, I'm going to specify block A and block B. And notice the mass I've subscripted with a B. And then there's a tension. And a tension is always due to a cable or a string. I'll call this a cable, a rope. Now it could also be due to like a an iron bar or a handle, like a metal handle, something that's not going to bend. And that tension can either be outward or inward. So it can be a tension or a compression. Go back to your statics class to think about that. This is, of course, acting on block B. Now you might want to say, well, block B is then pulling block A, but really it's not. Block B is not touching block A. So block B cannot exert a force on block A. What it can do is exert a force on the rope, and that's what the tension is. So there'd be tension due to block B acting on the rope, and then that tension will go all along the rope until finally it acts on block A. So there's the tension over here, T. All right, so that's a tension due to the cable acting on block A. And of course, there's a gravitational force, m sub a g. So that's gravity due to the Earth acting on block A. And there's a normal force, Fn. So a normal force due to the surface, could be a table, acting on block A. And those are all the forces acting on block A. We'll assume there's no friction. If there was friction, it might be going left or right. We're just not going to worry about it in this example at this point in time. So again, I've introduced tension now to the mix. There's 4 kinds of forces that we'll be working with, and you always want to define that force. Normal force, tension, gravity, and friction. Those are all of the forces that we'll be working with through the majority of this course. We may add 1 or 2 later on.